Good morning. My name is Nina Stark. I'm an assistant professor at Virginia Tech, and I work on coastal erosion and field site investigation in coastal environments. Today I want to talk about a rather special coastal environment, not as alien as Moon and Mars, I have to admit, but still a fairly special place, the Arctic. You may know that a third of our coastlines are actually Arctic permafrost coastlines. And we are encountering thawing of the coastlines, and that brings a number of issues. So one is actually release of carbon that is currently trapped within the frozen soil. But another one is that this leaves actually coastal soils much more vulnerable to erosion. Additionally, something we often don't really think about is if we are eroding the sediments there, where are they going? So where does the soil end up as soon as it is removed from the coastline? So knowing this process of climate change and thawing of permafrost coast may not be surprising to see that we are actually experiencing erosion rates in excess of 10 meters per year in the Arctic. This is, in fact, if you consider that you only have about 3 months of summer when erosion actually occurs, it's about 8 times faster than the really already pretty extreme erosion rates we are encountering in environments at the Gulf of Mexico. So it's very fast and very much even accelerating. So now you may say in the Arctic, a very remote place, does that even impact infrastructure? Do we really care about the place up there? But actually, there's quite a bit of infrastructure at jeopardy. More than 86% of native Alaskan villages are impacted by floods and erosion. Furthermore, there's discussion of dispersing these communities or relocating them. Imagine the town or city you're from would be subject to dispersion, that they're just saying you get moved to other places. Your village, your community gets split up, right? Obviously, that has extreme impacts on the society. There's also archaeological sites at jeopardy, as well as landfills are compromised. And the Arctic is actually hosting a fairly large oil and gas industry. And if you think about the extraction of hydrocarbon, that is directly impacted by erosion of the coast. Furthermore, the DoD has operations there, the DOE has operations there, the US long-range radar system sitting up at the Arctic. So there is actually quite a bit at stake. In fact, Clement et al. In 2013 suggested that more than $6 billion additional dollars have to go into sustaining and maintaining and changing infrastructure in the Arctic in the future. So in addition of these effects of coastal erosion, again, I want to point out, where is the sediment going? It has to be deposited somewhere. So that's really an issue for navigation. If you think about it, you never know how the bathymetry, where the water depths are the next day if you have the introduction of so much new soil. In particular, with this prospect of perhaps a longer open northwestern passage, this may impact navigation quite significantly. Additionally, you can imagine what that means for ecosystems if you have so much additional soil being deposited. Despite these needs, we actually know very little about the erosion processes as well as the sediment relocation processes in the Arctic. This conference has the subtitle Case Histories, so please let me take you to one location that I had the chance to visit in the framework of an expedition in 2014, Herschel Island, located in the southern Beaufort Sea in the Yukon Territory. So things we found are, for example, this is in the northwestern side of the island. And you found stretches of these silty cliffs with these exposed ice lenses. You can see very clearly that above the ice lenses, the slopes have failed, soil is eroded, and even beneath that. We don't really know, in particular underneath these ice lenses, is that mostly erosion due to freeze-thaw processes and then slope failure, or does that actually also go along with wave action that attack here the toe of the cliffs? I want to point out something more interesting. So the cliffs are silt, but you don't see that actually on the beach here. On the beach, you see it's all sandy and gravel. So that means that these finds are not deposited right in front. They're going somewhere. We don't really know where they're going yet. Probably offshore, maybe into the basin where no one is really impacted, but maybe not. Another location on the other side of the island, you find these massive retrogressive thaw slumps, and that is what this island is really famous for. It has some of the largest retrogressive thaw slumps in the world. In the lower left image, you see this little red dot. That's actually a person, right? So just to give you a scale of dimension. Retrogressive thaw slumps are slope failures that are triggered by freeze and thaw in ice-rich permafrost regions, and you see that they can extend up to 1 kilometer in size. So they're really massive, and you see in the upper image here that if you see the soil, it's actually the fines are almost flowing in a slurry like lava into the ocean, right? On the right images, you may notice this overhang. So this overhang is quite famous because it's actually equipped with a camera, and people are always predicting that it fails very soon. But this overhang is there almost for a decade, and it hasn't failed, but everything around it is failing. We don't really have a good explanation. We don't really understand how this works yet. Our work there was, in fact, more focused on the question is, where is this soil going? Obviously, it's being introduced into the ocean, in this case, the southern Beaufort Sea, but where is it being deposited? So this is just like one summary of the data we collected. And one thing I want to point out is we are in very shallow water with actually active wave action that changes very quickly. So that meant we are actually in an inflatable dinghy. In an inflatable dinghy, you don't have much options when it goes with equipment, so we just had a small grab sampler and we carried a portable freefall penetrometer to be able to navigate there. And even then, we had an incident where actually a boat was flipped by the surf and dumped into one of these muddy spots from the mud slumps. So a fairly risky environment to work in and very difficult to carry standard equipment that we are used to. So I just want to point out a few things. So you see here grain size distributions in the top, and that's obviously a large extrapolation. The black dots are actually the grab samples. And you see that a big problem is that there's not many, right? And that is, again, associated to the fact that it's so difficult to collect these samples there. We had one situation where we rowed out with a boat for 2 hours, and then we came back, the wave and wind condition changed, and it took us 6 hours to get back. You're in a survival suit. If you fall into the water, you have in the survival suit about 15 minutes before you pass out because of the cold. Right? So very challenging conditions to work in, and that's the reason why it's so hard to get these samples. But if you look into the data, you don't really see what you would expect. In front of slump D, what is one of the biggest and most active slumps, we actually do not find the fines we were expecting to find. It was pretty sandy up there. While we found a lot of finds towards the east, where actually the slumps are fairly stabilized. So how do they get there? Why do they get deposited there? Then on the lower image, in the dots and the circles, the colors are indicating estimates of sediment strength, in this case expressed in a proxy of quasi-static bearing capacity. And we again observe something similar. We didn't really find these very soft spots in front of the mud slumps, but sediment seemed to be transported away from these locations very quickly, and then in this case deposited again more towards the east, where they got trapped in a little cove. Another thing interesting, so the background of the lower image is a side scan sonar image. These darker brown colors should be coarser sediments, but that doesn't really match actually our grab samples. So we ended up with a situation that we actually were able to demonstrate. We get some measurements. We were also able to formulate somewhat of a hypothesis what is happening with the fate of the sediments. But to be honest, we came back with more questions than answers, right? So with that, I would like to conclude this very brief presentation with a call to and a challenge to our community of geotechnical engineers. Arctic coastal erosion is a problem for society, for infrastructure, as well as for changes associated to climate change. I truly believe that we as geotechnical engineers can make a difference and can contribute to finding solutions to this problem. But we have to get more engaged. We have to engage with the research community, the Arctic research community. We have to think to communicate more multidisciplinarity. This is not a one single discipline problem. We have to work together with other disciplines here, and we have to reach out and talk to them. And we also have to think about new methods and techniques, Because in challenging environments like that, we may not be able to run standard tests. We may have to develop new standards for working in such environments. And with this, thank you for your attention.